let's just go the whole thing.
Your view is that these cubes that James Hughes suggested are real. You're a realist with respect to the existence of these cubes, quantized space cubes, correct?
Correct, yeah.
A realist philosopher of science says that these things that we're talking about actually exist. They're actual physically existent things. So for you, this lattice of space is a physically existent thing.
Yes.
Okay.
And in fact, the spot unit shown in the upper right in this slide is actually the most fundamental object that we can get to so far in our studies of physics. But actually, this object must contain mechanisms at a much lower level. So we're talking about tomorrow's physics beyond binary mechanics, where the various parts, where there must be mechanisms in here to implement the equations of binary mechanics, the time development equations, so that quantum move or don't move according to those equations, which are simply a combination of binary numbers, the three things I mentioned, and functions and not functions. If you understand those three math ideas, you, by definition, you understand the equations of how the universe works. By the way, with those three math ideas, computer scientists accept that you can build a computer. You can build a completely functional computer that does everything that, in fact, the computers that we're using right now use those three basic ideas, and those are the only three math ideas that you really need to build the laptop or computer that you're looking at right now. And so if you could build a computer with those three ideas, why can't you build a whole universe with them?
And that's what makes you, that's where your theory of everything is coming from. So you're saying, as based on your realist assumption about the existence of these cubic lattice and the binary equations that you're using, that's your theory of everything. I'm just kind of being the devil's advocate a little bit. When you say 17th, yeah, see, this is where it gets a little bit. For one thing, I can't really claim to be really knowledgeable about a lot of this physics that you're talking about, where you're talking about quarks and leptons. Okay, now we're into an important thing: time development laws.
Time development laws here, there's 4 bit operations, and they're applied like a looping computer program. Like, for example, if you have a sticky key on your keyboard and you press it, and let's say you press the W key, and then in your word processor, the W is just repeating over and over and over again. And how do I stop this? And then you hit the escape key, That's an example in everyday experience that most of us have had of a sticking key on your keyboard that is looping over and over again. So that's what equation 17 at the bottom here is. That's the program of applying to the bit function, which is just the configuration of quanta in the volume, the 4 bit operations, scalar, unconditional, vector, and strong, these 4 bit operations to get a new state. So our universe is basically a looping computer program that is looping these 4 bit operations over and over again. If that program were to stop, because let's say whoever it is in charge of all of this needs to do some maintenance on the universe or whatever, and it's just stopped for a period of time and then starts up again, we'd have no way of knowing that, would we? We'd have absolutely no way to know.
With respect to this particular slide, it starts with equation 7. Where are equations 1 to 6?
For any physical theory, there are 2 things that you need, and only 2. You don't need 3 or 4 or 5, just 2 things.
Okay, so this is
a definition of system state and a definition of the time development of that system state.
Right. Okay, so these are all binary computer type equations. They're not normally we would think of as equation of motion would be m equals ma, and you'd get a
Right.
differential equation and use calculus.
Those are equations like of Newton, which are on the observational level. Those equations don't tell you how something moves, or they don't tell you why a certain element has a certain mass or a certain object has a certain mass. They don't tell you that. Nor do they even tell you that there's an absolute frame of reference in order to quantify acceleration. So Newton was the beginning of step one in all physics, basically, which is to just describe the phenomena, observational work, not what the mechanism of how the phenomena actually occurs. All right. Like, for example, I can describe a cockroach running across a table in terms of its position. If I have a grid, or let's say the cockroach is running across a chessboard, so I can count the number of squares he crosses and so forth. That's observation. That doesn't tell me how the cockroach actually moves his legs, that there's in fact a neural network in the cockroach to coordinate signals to the muscles, and there are contractile proteins which in fact can slide the filaments back and forth and in effect make the legs extend and move. That's where the mechanism of motion comes in. So Newton didn't even get close to that. He was talking about, let's just describe what happens the best we can. And that was a very important step. I'm not minimizing that in any manner, shape, or form. But the next step is, well, then how do things move? All right. See, the biologists are not content with saying the cockroach runs across the chessboard, and I can actually photograph that with my video camera or my phone, and I can then look at the frames and tell you how fast he moved and so forth and so on. But no, in biology, the scientists working there are interested, well, how does that sucker move? How do those legs move? See? So all I'm saying is maybe physicists should be as inquisitive as biologists are. I see binary mechanics as a step in advancing physics as a science. Let's get down to actually our best appreciation of what the mechanisms are. And if you can show me any phenomena whatsoever that these equations do not account for, well, then we've got some real problems. Something is wrong or incorrect, either completely or partially, and needs to be adjusted. And there are, even in these equations, for example, I pointed out there's certain things that are still not nailed down in my own mind. The bit operations order in the equation 17 here at the bottom of this slide, I'm not certain that that is. There only could be one bit operation order which is correct, because we know from data that I presented yesterday and much other data that I have that these operations do not commute. That means, in mathematically speaking, that if you change the order of the operations on your system state, you get different results. So it's only possible that one of these bit orders is in fact the physically correct ones.
In your theory, there's more than absolute space. You have absolute time, I think.
Yes. What I have assumed in the equation 17 that I showed a moment ago is that each of those 4-bit operations takes the same amount of time. That's purely an assumption. That could be wrong. Okay?
Okay, but in your theory, the time unit is like the clock on a computer, and when the computer gives the time pulse, then the computer changes its state to another state, and the state that it's changed to is defined by the equations that you're talking about.
Yes. Now, I don't believe myself that in this vast universe that we have, that there's a sort of a central clock location as is analogical to that of a computer, where there's a crystal there which is ticking, and that tick is detected and sent as a signal to synchronize everything in a computer's operation. I don't think that's what's going on here. Somehow, I think that at the local level, these processes, being binary processes, just occur at a particular rate, which is in fact the time constant. I think that these three values here are a unique set of values and the only set of values which satisfy all of these equations to get what I call the secondary constants, such as Planck's constant, electric charge, E, and so forth.